All right. A 0.15 Tesla bar magnet is removed from a circular coil of wire with 500 loops, a radius of 0.09 meters in 1.1 seconds. Call the direction it's removed out of the page. Assume the pole removed is north. A. Find the induced EMF in the coil caused by the magnet. B. Figure out the direction that the induced current will travel. So I want you guys to try to set this one up on your own. Do your knowns and unknowns first. See if you can figure out what equation to use. See if you can set it up. So start on that on your own first. I'll come around if you're stuck. If you're just like, I got no idea, Mr. B. Okay, best place to start is knowns and unknowns. So we have the number of loops, which is 500. We've got the radius, which is 0.09. We've got the time it takes, 1.1 seconds. And then we've got this magnetic field, which is 0.15. And the problem asks us to solve for EMF. Okay, as soon as I see EMF, I'm like, psh, there's only one problem with EMF. It has to be this one, right? There's only one equation with EMF, so it's got to be this. So electromotive force is what we're solving for. Remember, electromotive force is basically just voltage. It's just an induced voltage. So the equation is negative N times A. A is the area. So I wasn't given the area, I was given the radius. So I look at my equations and I say the area of the better be on. Oh, it is. Area of a circle is pi r squared. So pi times 0.09 squared times delta B. Now delta B is the change in magnetic field. Well, all I have is the value for the magnetic field. And this keyword, removed. So the fact that it's removed means I take the field out. It goes to 0. So the change in the magnetic field is negative 0.15. Because that's how much it changes by. It changes by 0.15, and it's 0.15 going down, not 0.15 going up. And then the time is pretty easy. It's 1.1. So when you're ready to solve, I get rid of the negative signs. And let's see, 500 times pi, where are you, pi? There you are, pi, times 0.09 squared times 0.15 divided by 1.1 gives me 1.74 volts.
I got 5.372.
Did you square the 0.09?
That's the answer? 1.7.
Yeah, that's the answer, 1.7.
Oh, because
I'm assuming,
I rounded around to here.
and that's fine. Yeah, that's fine. Okay. Any other questions on this before we move on to B? B. Okay. B. B wants to know the direction. So here's how we do the direction. All right, here's my circular coil of wire. I'm removing the field from it. The thing to keep in mind is that the induced field is always in the opposite direction. So my field went down, but my induced voltage is up, which means the induced field is in. So always keep that in mind. The induced field is always opposite. So if I remove the field, the induced field is in. All I have to do from that point then is wrap my thumb around. This is the first right-hand rule. So first right-hand rule, thumb is the direction of the current. Fingers twist in the direction of the field. So here's my fingers. They're already in the direction of the field going into the paper. again, reset, assume, call out of the page the removed. So into the page is the induced field. I lay my thumb, and my thumb is going clockwise.